All right, today we're diving into a topic that, believe it or not, governs pretty much everything. We're talking about your morning coffee, the engine in your car, and even the ultimate fate of the universe itself. We're talking about the fundamental rules of energy, the laws of thermodynamics. So let's start with a really simple mystery, one you've probably noticed a million times. You pour a hot cup of coffee, you get distracted, and when you come back, it's cold. But have you ever seen a cold cup of coffee on your desk suddenly, spontaneously heat itself back up? Of course not. It's a one-way street. But why? The answer is hiding in these amazing rules. And that, right there, is the heart of thermodynamics. On one hand, it's the science of how energy moves around and changes form. But the really cool part is that it allows us to predict whether something, like our coffee cooling down, is going to happen all by itself. Scientists have a great word for this: spontaneity. Okay, so before we can jump into the big laws, we've got to learn the lingo. It's pretty straightforward, but we need to be on the same page about what exactly we're talking about when we talk about energy. The easiest way to think about it is this. You just draw an imaginary box around whatever you're studying. It could be a beaker of chemicals, a car engine, or, our cup of coffee. Everything inside that box is what we call the system, and absolutely everything else in the universe, that's the surroundings. So these boxes, or systems, come in three main flavors. First up, you've got an open system. This is like an uncovered pot of boiling water on the stove. It's sharing energy, heat, with the kitchen, and it's also sharing matter, because steam is literally escaping into the air. But what happens if you slap a lid on that pot? Well, now you've got yourself a closed system. The matter, all that water vapor, is trapped inside. It can't get out, but energy, the heat, can still pass right through the walls of the pot into the room. And then there's the ideal situation, the isolated system. The best analogy for this is a perfect thermos. In theory, it's so well insulated that nothing gets in or out. No energy, no matter. It is completely cut off from its surroundings. Okay, one last bit of vocab, I promise, before we get to the laws. We need to talk about properties. Some properties, called extensive properties, depend on how much stuff you have, like mass or volume. More stuff, more mass. But intensive properties, like temperature, don't care about the amount. A tiny drop of boiling water and a giant vat of it are both at the exact same temperature. All right, we've got the vocabulary down. Now we can finally tackle the first great rule of energy. And you can really think of this as the universe's most basic, unbreakable accounting principle. So every single system we define has its own sort of energy bank account. Scientists call this its internal energy, and they usually use the letter U for it. It's just the grand total of every bit of energy from all the little particles buzzing around inside our system. So, if you want to change the balance in that energy account, how do you do it? Well, it turns out there are only two ways to make a deposit or a withdrawal. The first is heat, which is just energy flowing because of a temperature difference. The second is work, which is pretty much every other way you can transfer energy, like pushing something or using a magnetic field. And this all leads us to the first law, wrapped up in one beautifully simple equation. Delta U equals Q plus W. That's it. The change in a system's internal energy is simply the heat you add to it, plus the work you do on it. Perfect bookkeeping, every single time. But here's the really big takeaway, the thing you absolutely need to remember. The first law is basically saying energy is conserved. You cannot create it from thin air, and you can't make it just vanish. All you can do is move it around or change what it looks like. This is exactly why those perpetual motion machines you see online, they're impossible. You just can't get more energy out than you put in. Okay, let's put this to the test with a super quick example. Imagine our system gets a deposit of 50 joules of heat. On top of that, we do 10 joules of work on it, so that's another deposit. What's the change in its internal energy? Yep, you just add them up. 50 joules from heat plus 10 joules from work, that's 60 joules total. The system's energy account has gone up by exactly 60 joules. See? Simple. The books are balanced, the first law holds. Okay, so the first law is awesome for keeping track of the energy, making sure the accounting is right, but it's got this huge blind spot. It tells us nothing about why things happen in one direction and not the other. It doesn't explain the arrow of time. For that, we need the second law. Let's go all the way back to that coffee. The hot coffee cools down and the air in the room warms up a little.
Energy is perfectly conserved, so the first law is happy. But here's the crazy thing. The reverse process, the now cold coffee, spontaneously sucking heat out of the air and getting hot again, that would also perfectly obey the first law. But it never, ever happens. So we're obviously missing a crucial rule here. And that missing rule is all about a concept called entropy. You've probably heard of it. Entropy, which gets the letter S, is basically a scientific way of measuring disorder, or randomness, or even just messiness. And it turns out the universe has this deep, fundamental preference for things to get messier and more disordered over time.
And that brings us right to the second law. It states that for any process that just happens on its own, the total entropy, the total disorder of the universe has to go up, always. Heat flows from your hot coffee to the cold room because that spreads the energy out, increasing the total messiness. This is the law that gives time its direction. This is why coffee always gets cold.
So now we've got these two powerful forces. The first law demands that the energy books stay balanced. The second law demands that the universe gets more disordered. So how do these two giant rules work together to decide what actually happens in the real world?
Well, this is where a brilliant concept called Gibbs free energy comes to the rescue. Think of it as the ultimate decider. It's a clever formula that combines the heat change of a system, which we call enthalpy, with the disorder change, the entropy. And the rule is just beautiful in its simplicity. If the final number, the change in Gibbs free energy, is negative, the process is a go. It will happen all by itself. And this table right here, this is the ultimate cheat sheet for predicting the future. Look at that top row. If a process releases heat and it gets more disordered, well, that's a win-win for both laws. It's always going to happen. But now check out the bottom row. What if a process needs to absorb heat, but it increases disorder, like ice melting into water? Now there's a conflict. And in that case, temperature becomes the tiebreaker. It will only happen if it's hot enough for that powerful drive towards disorder to win out. And all of this leaves us with one final, kind of mind-blowing thought. The second law tells us that the total disorder of the entire universe is always relentlessly increasing. So, if you follow that one-way street of ever-increasing chaos all the way to its final destination, what happens in the very end? What does that ultimate maximum messiness state of the universe even look like? That's definitely something to think about.